degrees of freedom, given we have this model here. So, and we would like to discuss this briefly, how it looks like, how this test basically would look like if we would use the LM test instead. Because under certain circumstances, it can be easier to implement the LM test instead of the wall test. Yeah? Now we are in the LM test. And LM stands for Legrand multiplier. The Legrand multiplier test. Yeah? So how does it look like if we implement the LM test instead? And again, the reference distribution is exactly the same, but how it's derived is different. So what we would do if we would like to have the same setup here, yeah? So we would like to test if the three-factor model, if these two additional regressors here, if they add value. So we are interested in if beta 2 and beta 3, if they are significant. Yeah? Under the null hypothesis, again, they are 0, and under the alternative hypothesis, at least one of them is significant. Yeah? So how would we set up the LM test? So what we would do first is, the first step is we run this model under the null hypothesis. So under the null hypothesis, these guys here are 0, right? So what we do is we have our on the left-hand side again the excess portfolio returns the excess equity portfolio returns denoted as YT, and we would regress it on an intercept term alpha plus beta 1 times x1t. So we would regress it only on the market factor, because under the null hypothesis this is the correct model. And because it's a regression model, we add here an error term which we define as ET. And obviously it's different from this guy in that equation, obviously. So then, how does our X matrix here look like? It's very simple. It's a model. Our X matrix has the vector of 1s in the first column and the excess market factor x11, x12 until x1 capital T is the regressor, is the second regressor here. So this is our X matrix is simply in this model here T by 2 has the dimension T by 2. Yeah? Our parameter vector beta hat obviously is a 2 by 1 vector which has the alpha of this equation and the beta 1 of this equation in a 2 by 1 vector. Yeah? Very simple. So then we know how to estimate this model. Yeah? So we get the corresponding parameters by x transposed x inverted x transposed y. Yeah? Very simple. And we know also that we can estimate our residual vector denoted as E hat simply by our y vector minus our X matrix times our beta hat, or our vector that comprises these two estimated parameters. Yeah? So very simple. So that's how we get the residual estimates, the estimated vector of residuals from our null hypothesis model. Okay? So the second step is then, so we regress our estimated residuals from the null model on the market factor, on the variable from the null model and the alternative model. So what we do is basically we have the regression equation E hat t is equal to, now let's call it delta 0, an intercept term, plus delta 1 times x1t plus delta 2 times x2t times plus delta 3 times x3t. And because it's a regression equation, we also add a residual, and now we have here used u, here is we used e. Now let's call it epsilon t. Yeah? And again, our assumption is that our epsilon t is distributed as normal with zero mean and sigma square epsilon as corresponding variance. So in this regression model here, obviously our our regressor matrix has ones, a vector of ones. In the first column, yeah, we have the excess market returns. In the second column, x11, x12, and so on, and x1 capital T. Now our second regressor is obviously the size factor, our x denoted as x2, starting with x21, x22, and so on, until we reach x2 capital T. And finally, we have a third regressor, fourth regressor, obviously, which is the value factor, yeah? Our x31, x32, until we reach x3 capital T. So what we have here is then our x becomes now in this regression equation a t by 4 matrix, yeah? And our corresponding parameter vector beta hat, yeah, for this regression equation consists obviously of the corresponding parameters delta 0, delta 1, delta 2, delta 3. So it starts with delta 0 hat, delta 1 hat, delta 2 hat, and delta 3 hat. So what we have is that our beta hat is a 4 by 1 vector. Yeah? So we get the corresponding regression residuals of this equation here, yeah, our epsilon t, obviously by very simple e hat, yeah, minus, because e hat is now our dependent variable in this equation, so e hat minus this matrix X times this parameter vector beta hat of the auxiliary regression equation. Yeah? So we need this residual vector in order to compound the R square of this auxiliary regression equation. Yeah? So our R square of this auxiliary regression is defined as 1 minus this epsilon hat transposed times itself, yeah, so the estimated residual vector of that auxiliary regression equation, divided by e hat transposed times e hat. Yeah, which is obviously the dependent variable of our auxiliary regression. Yeah, that is the R square of the auxiliary regression equation. Yeah. So the third step is then, yeah, the third step is then that our test statistic lambda is given by t times r square, yeah, this r square. And this follows under the null hypothesis a chi-square distribution with 2 degrees of freedom. Yeah. Same test statistic, obviously. Yeah? And t, capital T, is the number of sample observations that we have. Yeah? And this is an asymptotical test. So there are 2 approaches. There are actually more than 2 approaches, but we discuss only 2 in this lecture. How to test if these 2 parameters here are different from 0. Yeah? And this is one of these approaches. It's the LM test. So obviously the difference is that the first step is that we implement the model under the null hypothesis. Yeah? We start with the null hypothesis model. Yeah? We grab the regression residuals from the null model, yeah? And we regress it on the whole model. Yeah, that's the second step. Yeah. So then we grab the regression residuals of this auxiliary regression, yeah, in order to get the r squared, yeah, which is the coefficient of determination, yeah, which is then given by this formula here. And then we know that the test statistic is distributed as capital T, that's its number of observations, times these r squared from the auxiliary regression. Yeah. So, and of course the model can look different, so, but this is basically the approach how you would implement this test. Yeah? And in some circumstances it can be easier to implement the LM test instead of using the wall test, yeah? Because obviously we start here with the model under the null hypothesis. And why this test is distributed as chi-square, so this is derived from Godfrey in his book. So if you would like to read it, I can give you the reference for that as well. But yeah, for us it's important to know this approach, okay? Because we just want to apply basically this test to our framework. And as you see, for the if you compare basically the arch LM test and the standard LM test, so these we remember obviously here this formula that we have an auxiliary regression, and our test statistic lambda is then basically our number of observations capital T times this r square from the auxiliary regression. This is basically what these two tests have in common. Yeah. So this is basically the econometric framework that we need for this course, and what we'll do next is we will discuss the momentum anomaly, yeah, and how we implement it basically, and then afterwards we would like to discuss some basic commands in MATLAB, how they work, and basically the most important commands that we basically will need when we operate with MATLAB. And then after that we will start to use MATLAB, knowing basically all this background